Relational database design is built on the mathematical concept of functional dependencies. This rule states that if every value of attribute A is associated with exactly one value of attribute B, then A determines B. Some dependencies are trivial. For instance, if you know a student's roll number and their name, you already know their roll number. Because the result is just a subset of the starting data, these rules provide no new information for our design. We focus instead on non-trivial dependencies. In this case, the roll number, the input, determines a completely different attribute, the student name. These are the specific rules we use to organize data. Identifying these non-trivial dependencies is the first step in the design process, providing the raw material for the normalization algorithms that follow. In a table with dozens of columns, we cannot rely on intuition to find the primary key. Instead, we use a systematic process called attribute closure to find which attributes determine the rest of the set. First, we look at the right side of our dependency rules. Notice that while B, C, and D are all determined by something else, attribute A is not. This means A must be a component of our candidate key. Now we compute the closure of A. Based on our rules, A determines B determines C, and C determines D. Because the starting attribute A allows us to derive every other attribute in the table, A is our candidate key. This algorithm provides a mathematical guarantee that the chosen key can uniquely identify every row in the relation. Sometimes a single attribute is not enough to determine the entire set. If the closure of our starting attribute doesn't include every column, we have to look for composite keys. Consider these new rules. Attribute B is the only one missing from the right side, but the closure of B is just B itself. It doesn't determine any other data on its own. This means the key must be composite. Pause here and compute the closures for these three pairs, AB, BC, and BE. Testing the first pair, AB, we find that it determines C, and C determines D. We now have the full set of attributes. Performing the same steps for BC and BD shows that they also determine the entire set. In this schema, we have three distinct candidate keys. Identifying every candidate key is essential, as any of these could serve as the primary anchor for the table's data. For second normal form, non-key attributes must depend on the whole primary key. Here, the student name repeats because it depends only on roll number, a partial dependency. To fix this, we move offending attributes into distinct tables, student name to a student table, course name to a course table. This reorganization ensures that a student's name is stored in only one place. By removing partial dependencies, we ensure the data is non-redundant. These three steps, filtering for non-trivial dependencies, calculating attribute closures, and decomposing partial dependencies, form the mechanical basis of consistent database design.